Designating extension boards as simple electronic appliances greatly undervalues their utility. These versatile devices eliminate the need to scour for distant power outlets, while also eliminating household disputes over who gets to charge their device first. Multiple devices can be fused together through these boards, which consequently become critical activity centers. This practical, connect-and-use device operates on a straightforward scientific basis. An extension board, also known as a power strip, is essentially composed of numerous sockets independently connected to a flexible power cable and held within a shockproof plastic shell. Its role is to draw power from wall outlets and distribute it evenly among devices connected to its multiple sockets. Designs of extension boards can differ, with some featuring individual switches and LED lights to mark the sockets in use. However, their key attribute is the equal allocation of power among all connected devices. This ensures seamless functioning of all devices and is achieved by linking the individual sockets in parallel with each other, much like a power distribution hub. Electric current flows between 2 points with voltage differences, much like water flowing across areas with altitude differences. For this current to flow through a circuit, it must be attached to a power supply that generates a voltage difference, also referred to as a potential difference. The flow of this current through a circuit obeys Ohm's law, which states that voltage is the product of the circuit's resistance and the flowing current, represented in mathematical terms as V equals IR. All appliances connected in a circuit draw current, thereby causing resistance to any further current flow. Thus, these appliances are represented correspondingly. Electrical circuits are typically classified into 2 categories: series or parallel, based on the arrangement of their resistances. On the one hand, in series circuits, the entire current flows through all resistances connected in sequence. A drawback of this system is the disruption of the entire circuit upon the failure of one appliance. On the other hand, in parallel circuits, resistances are connected to a common power source, but follow individual, dedicated paths, and this configuration is beneficially employed in extension boards. Although extension boards operate on a basic principle, their design involves careful consideration of the power requirements of connected appliances. The boards require surge protection to prevent electrical damage and short-circuiting, since parallel circuits can draw hefty currents. The connected wires, typically made from excellent conductors like copper, as well as the branching wires and electrical contacts, all need to withstand the demands of the connected appliances. Moreover, circuits that draw large amounts of current need safety precautions, such as fuses made of poor conductors, to prevent equipment damage. With the advent of miniature circuit breakers, MCBs, in modern electrical systems, an extra layer of security has been added against electrical faults. Furthermore, extension boards that support numerous devices often have a 3-pin plug for grounding, effectively diverting any excess current onto a low-potential surface. As far as advanced options go, it is expected that future extension technology will be built around power supply options integrating data transfer capabilities, like USB and HDMI, gradually replacing traditional wall outlets. Even so, until we notice a major shift towards wireless charging and self-powered devices, extension boards will continue to play a pivotal role in catering to our diverse power supply needs.